All right, welcome to a quick video reviewing logs and exponentials. And I'm going to have everything bookmarked in the description so you can skip around to any part of this video that you need. But you can see we're going to talk about just a reminder of what logs are and how they relate to exponents. We're going to look at the properties of logs. We'll first prove them, and then we'll look at expanding and condensing and using the change of base formula. We're going to solve exponential equations, and they kind of fall into two flavors. One where you can just equate the bases and you don't have to use logs at all, and the other one when you do have to use logs. And then finally, we'll end with solving log equations. And again, those come in two flavors. Either every term has a log, or at least one term doesn't have a log. So that's kind of the goal of today, and let's just jump in. So an overview of logs and what they are and everything. This is the definition of a log right here in this box. And so you read this as log base b of a equals c. And this means the same exact thing as saying b to the power of c equals a. They're equivalent statements. Um, you need to get comfortable writing back and forth between the two different forms. And I call it around the world. If you start at the base and go around the equal sign, it kind of tells you the order to put things in. So if you're going to change a log into an exponential, start at the base and go around the equal sign, and it's b to the power of c equals a. And that's right here. And you can see it actually works going the other way too. If on this side we start at the base and go around the equal sign, it will put everything back in this. Log base b of a equals c. So always start at the base, go around the equal sign. And a lot of people just call that around the world. Um, Also, take a note, the answer to a log is the same thing as the exponent on the exponential. So a lot of times you'll also hear people call logs exponential exponents for that reason, because the answer to a log is just the exponent. Okay, so with that in mind, see if you can remember how to evaluate these. I encourage you to pause the video before I reveal the answers, but give them a shot, think about them, and we'll go over the answers real quick. Okay, so if we take a look at this one, some people in the beginning, especially if it's been a while since you've done logs, it helps to at least think about the exponential equivalent. And again, if you start at the base and go around the equal sign, this means 3 to what power is 9? So think 3 to what power is 9? And the answer is 2. So then the next one, if we think 10 to what power is 10,000? The answer is 4. With C, if we think 5 to what power equals 1? The answer is 0. And ideally, you want to get to the point where you can do these problems without writing out the think statement. I keep writing think because ideally you want to get to the point where you're thinking this in your head. You're not actually working it out. Now, the second column gets a little tricky. Again, pause the video if you're like, okay, I think I got it. I want to try these. They are a little trickier, but give them a shot. And here are the answers. For this one, we're going to think 25 to what power is 5? Well, the square root of 25 is 5. And then we know square roots are the same thing as an exponent of 1/2. Okay, try E. Think 4 to what power is 1/16? Like I said, this one's a little tricky. So first of all, we know 4 squared is 16. So 4 to the power of 2, but it's 16's in the denominator, so we also had to flip it. So negative because it turned into a fraction, but 4 squared is 16. All right, let's try the last one. Think 36 to what power is 1/6? The whole number turned into a fraction, so it had to flip. It's negative. 36 turned into 6 by taking the square root. So that's -1/2. Okay, so there's evaluating. Now there are some special types of logs. Common logs, these have a base 10. So if you ever have log base 10 of something, I'll just say 3, that's called a common log. Now, sometimes, because it's a common log, it's common to leave out, I shouldn't put it, that was supposed to be a circle, not a 0, but there's no base written. And so with common logs, the base is optional. So when the base is 10, it is optional to write the base. Natural logs, these guys have a base e, the natural base. And so we write them as natural log of something. I'll just say natural log of x. Natural log, this is an L. In textbooks, you're going to see a natural log written as ln, it's printed. A lot of students misinterpret that as an I. That is not an I, that is an L. So when I handwrite it, I always make a cursive L to make it clear. It's ln, not in. There is no such thing as in. So don't write it. It's ln. And this is the same thing as saying log base e of x. However, don't write it this way. I mean, yes, it does mean the same thing as the natural log of x. However, we never write it this way. If your base is e, it's written as ln x. So yeah, there's common logs and natural logs. All right, some log values to know. If you have any base of 1, log base b of 1, any base to what power is going to be 1? And the answer is going to be 0. So, and actually I should have defined this up above. We call the whatever's in this place, this is called the argument. So if your argument is 1, the answer to the log is 0. Okay, the next one, b to what power would be b? And that answer is 1. So if your base of the log matches the argument, the answer is always 1. If you have log base b of b to the x, the answer is just x. And then similarly, if you have b to the power of log base b of x, the answer is x. And the reason for that, logs and exponentials are inverses of each other. They undo each other. So if your base of the log matches the base of the exponent, they'll cancel out and you're just left with x. And then similarly, if your base of the exponent matches the base of the log, they cancel each other out, they undo each other, and you're just left with x. And these same rules, because natural logs are just logs, these same rules will also work with natural logs. A lot of people think, they get, especially in the beginning, they forget that they're really just logs. So the natural log of 1 is 0. The natural log of e is 1. The natural log of e to the x is x, and e to the natural log of x is x. So those are things to know. Get good at recognizing them. And then finally, to finish out this section, this is the longest section, by the way, I think. Restrictions on logs. And I'm not going to go into it in this video why. It has to do with them coming from exponentials and all that. But anyway, just trust me on this. A will always exist in the set of real numbers, and B must be a positive number, real number. C will always be a positive real number. B and C cannot be 0, and they cannot be negative numbers. So your base and your argument for a log must always be positive. All right, so that finishes that. Let's go on. Okay, so properties of logs. There's 4 properties to know. The fourth one's, I mean, some people don't call it a property. I call it a property. We'll put it in this chunk. Here are the properties. The product property of log says if you are taking the log of a product, then that is equal to log base b of m plus log base b of n. So this single log can turn into multiple logs. And then the quotient property is log base b of a quotient, m over n, and that can be expanded into 2 logs using subtraction. These 2 properties come from the property of exponents. When you are multiplying with the same base, you add the exponents. Or when you divide with the same base, you subtract the exponents. We're going to prove it really quickly in a moment. The power property, oh goodness, that is log base b of a to the c. So if you have a power on your entire argument, you can pull that exponent out in front and multiply it by the log. And then finally, the change of base formula, that one, let's see here, we get log base b of a. It will literally let you change a log that's in terms of one base into any other base. So I'm just going to bring a new variable in here, c, and we can say it's log base b of c over log base b of, oops, let's try that, log base c of b. So we were in base b. We have now changed this to an expression in terms of a new base. Notice that the old argument is the argument in the numerator. The old base is the argument in the denominator. There's your properties of logs. Some quick proofs. So a proof of the product property. If we start with this, I'm going to define m to be log base b of a and n to be log base b of c. Using that around the world, start at the base, go around the equals sign. B to the power of m is equal to a. That's where this comes from. And then b to the power of n is equal to c. And that's where this comes from. And then I can multiply. I can do b to the m times b to the n is b to the m plus n. Just using our rule for exponents. But remember, b to the m is the same thing as a, and b to the n is the same thing as c. That's from right here. Now, if I take the log base b of both sides, I get this. And on the right-hand side, remember our properties from above, the base of the log matches the base of the exponent. So these cancel out, and you're just left with the exponent. But remember that m, in the very beginning, I defined it to be log base b of a, and n, I defined to be log base b of c, and that's exactly our power product, or power property. Sorry, product property. So log base b of a product is log base b of the first factor plus log base b of the second factor. All right, and then the quotient rule, you can do it very similarly. You just change this to a division and then see what happens, but you'll do it very similarly. You want to do it for fun? I encourage you to do it. We're going to take a look at the power property now. So the power property, if I again define m to be log base b of a, then from around the world, we know b to the power of m is equal to a right there. So starting with that, if I raise both sides to the power of c, my rules of exponents, when I have a power to a power, I can multiply the exponents. Now I'm going to take the log base b of both sides. The base of the log matches the base of the exponent, so they cancel out. This side, they stay the same. And then we know that m is log base b of a. And that is our power property. So again, if you have an exponent on your argument, you can move that exponent out in front and multiply it by the log. Or similarly, if you have a coefficient in front of the log, that can move as an exponent on the argument. There's power property. And then finally, the change of base formula. Once again, I'm going to start off with m equaling log base b of a around the world. I know that b to the power of m is a. So if I start with that, and then remember, change of base, I'm going to introduce a brand new base. So I'm going to take log base c of a new base of each side. Using that power property we just proved, I can move this m out in front and multiply it by the log. And if I divide both sides by log base c of b, I get, and then replace m with what it equaled, I get the change of base formula. So if you need to take more time looking at those screens, feel free, go ahead. But now I'm going to move on to just using the properties a little bit. So let's use a calculator to evaluate the following. Okay, if we take a look at the first one says log of 3. There is no base written. So remember, that means that there is an invisible base 10. Now, if you take a look at your calculator, there is a button that says log, but there is no base written on that button. That's because that button is specifically for log 10, log base 10. It's a common log button. So to evaluate this on the calculator, it's very simple. You literally just press the log button, followed by the 3 button, and it gives you the answer, which is approximately 0.477. Okay, the second one, natural log of 3. And again, if you look at your calculator, there actually is a button that says ln. And so to evaluate this, very simple. You simply hit the button that says ln, then hit the 3 button, and your calculator will tell you that this is approximately equal to 1.09. Well, I guess it would round to 99, 98 or 99, depending if you're following the AP rules for truncate or rounding. I'm going to truncate. I'm just going to cut it off. Okay, so the last one is in base 2. And there is no base 2 button on the calculator. And so how do we do this if we can only evaluate using base 10 or base E? That's why we have a change of base formula. Yay! So I'm going to go ahead and change this to, you can either use common logs, and if we change it using common logs, it's going to look like log base 10 of 3 over log base 10 of 2. Or we can use natural logs and say natural log of 3 over natural log of 2. And that's using the change of base formula. And I encourage you to try both of them. You'll see you get the same exact answer. And the answer is approximately 1.584. And that's it. So I'm going to go ahead and just show you really quickly on the calculator, and then we'll move on. Here we are in the calculator, and here are the buttons on the side for log and natural log. You know, scientific calculators also have these same buttons. You don't need a graphing calculator. But to do that first problem, log base 10 of 3, you literally just do log base 10 of 3. And there's the answer. And the second one, to do natural log, you do natural log of 3. And there's your answer. And then for the last one, for log base 2 of 3, when you change it using common logs, you do log of 3. Remember to close your parentheses and then divide by log of 2. And there's that answer. And look, if I did natural log of 3 divided by natural log of 2, whoa, we get the same thing. So it really does work. Now, before I go on, I do want to show you a little secret. It is important to know the change of base formula because not all calculators there are some calculators that can do other bases. Any scientific or graphing calculator can do log base 10 and log base e. Some can do other bases as well. So I'm going to show you a little trick because ours is one of them. But you do have to know the change of base formula because there are other uses for it, and you will see it in this unit. So if I go into math and I just keep scrolling down, look at that log base. I'm going to go ahead and hit enter. Look at that. It's got a little template. Log base 2 of 3. And there's that same exact answer. So our calculator is one of those that can do other bases, but I still want you to practice using change of base formula. There's a couple problems on your assignment. Okay, let's go back to the notes. Okay, let's practice expanding now. So when you're expanding, in general, start with a power property when you can. And remember, the power property is if you have an exponent on your entire argument. We do have an exponent. However, this exponent is not on the entire argument. It's only on this factor here. So we can't use a power property first. Instead, everything's being separated by the big division. And so we'll do a quotient property first that says we can expand using the same base. We will have the numerator minus log base 3 of the denominator. So that was using the quotient property. Okay, let's look at this term now. Again, we do have an exponent, but it's still not on the entire argument. It's only on the x minus 2. So we're going to use the fact that we have a product. And we're going to take this term and split it up into log base x plus, log base 3 of x plus log base 3 of x minus 2 squared. And then for this term, remember that the 1/2, that does mean the square root does mean an exponent of 1/2. So we can use the power property to move that 1/2 out in front. And then we have this. And now, finally, this 2 is on the entire argument. So I can put that 2 out in front using the power property. And I finally have my answer. And that's pretty much it. So there's expanding, an example of expanding. You got some to practice. Now let's take a look at condensing. So for condensing, you do that backwards. Now, once you get the hang of this, you can actually do it in fewer steps, maybe even all in one step. I am going to show you a little shortcut here. The first thing I recommend, though, is if you have any numbers, any coefficients in front of the logs, move them as an exponent. So I'm going to take this guy and also move it as an exponent. I'm going to have the natural log of x minus the natural log. Now in this case, my exponent of 1/2, I can write as an exponent of 1/2 or make it a square root. And either way is fine. There's no right or wrong answer there. I'm going to go ahead and just make it a square root. And then the next term, I'm going to move that 5 as an exponent on my argument. And then have that. All right, I'm going to, like I said, because this is just a review, I'm going to go ahead and show you a shortcut that you can do. Actually, well, no, I take it back. Let's go ahead and do this the long way, but then I'll show you the shortcut at the end. If I take it 2 terms at a time, so this is a minus sign, that means I can condense to a single log using division. So it'll be natural log of x over the square root of 2x minus 3. But then I still have all of this. Okay, now I'm going to take these two, and because there's a plus sign in between, I'm going to multiply this by this. I'm going to get natural log of x times x plus 2 squared over the square root of 2x minus 3, but then I still have a minus natural log of w. Okay, when I take these last two, I'm going to divide by w, so I get natural log of x plus 2 squared over the square root of 2x minus 3. Now that would be divided by w, the whole thing, just the argument, I should say. But instead of dividing by w, I can multiply by the reciprocal, and that will simplify it a little bit. So I'm going to multiply by the reciprocal and get this, and then I get my final answer. And in the bottom, I would have w times the square root of 2x minus 3. And there is my answer. So what's the shortcut, you ask? Let's go back. Let's look at this line. After we took those coefficients and made them exponents. Notice any term that was positive, so this was a positive log here, this was a positive log here. These arguments went in the numerator, and any log that was negative, so this one and this one, these arguments went in the denominator. And that's always going to happen. So if you want to jump from this line and just go all the way down there, feel free. And you will see in this class, we have some uses for going both ways, for expanding and for condensing. So it's coming up. Okay, next big topic, solving exponential equations. So there's two flavors. You can either equate the bases or you can't. If you can equate the bases, you don't have to use logs to solve this. Okay, so how do we do this then? So like it implies, equate the bases. You want to rewrite the bases so they're equal. And if we take a look right now at the bases, we have a base 2, a base 8, and a base 1 over 32, and they all can be written as base 2. So I'm going to leave the first one the same, 2 to the 5th. 8 is the same thing as 2 cubed, but that's raised to the negative 2k. And 1 over 32 is the same as 2 to the negative 5th, and that's being raised to the negative 2k. And then I'm going to do some properties of exponents. So in the denominator here, when you have a power to a power, you can multiply the exponents, and you get 2 to the negative 6k. And then same thing here, you have a power to a power, you can multiply the exponents, and you get 2 to the positive 10k. And then we're going to do the same thing, move it over here. More properties of exponents. I've got division between the same base. That means I can subtract the exponents. And then over here, I still have 2 to the 10k. I can just rewrite that exponent on the left as 5 plus 6k. And once I have 2 to a power equals 2 to a power, the bases are equal, so the exponents have to equal. So we have 5 plus 6k equals 10k. And now we have a super simple equation to solve. Subtract 6k from both sides and divide by 4, and we have k is equal to 5/4. So the idea when you can equate the bases, rewrite the bases so they are the same, and then use your properties of exponents until you can get it down to a single base and exponent on each side. and then equate the exponents, and you solve it. So that's equating the bases. What do you do when you can't equate the bases? Well, we're going to have to do logs. But the first thing that you are going to want to do is you're going to want to isolate the base and the exponent in the problem. So in this problem, 4 and 7a minus 5 are my base and exponent. So I have to get rid of everything else. I'm going to add 6 onto both sides. Oh, arithmetic is hard. And then I'm going to divide by -3 on both sides, and we'll get positive 91/3. Now, at this point, there actually are two different ways of writing it. Actually, I could even say there's multiple different ways. Um, I'm going to show you both of them, and you can do either one on a test. Multiple choice, you got to know both so you know how to write, which way to go. You can always change one to the other using our change of base. This will all make sense in a second. But this is the one where you just have so many choices, and your answer is going to look very different depending on what you do. Anyway, one way you can do it is simply round the world it now. We want to get the variable out of the exponent. We have to undo exponents, and that's the whole purpose of logs. So if I start at the base and go around the equal sign to rewrite it in logarithmic form, I get log base 4 of 91/3 equals 7a minus 5. And now I can go ahead and just isolate the a. I will add 5 onto both sides, and then divide by 7. So we get a equals log, actually, let me move this, log base 4 of 91/3 plus 5 over 7. And then now you know how to use the change of base formula. If you needed to get a decimal approximation of this, even though it's in base 4, you could get that. Another way though is, and there's actually other ways than just this, but this will kind of give us some ideas. Another way, rather than around the world and rewriting it using the same bases in the problem, you can start with a calculator ready base, log of base 10 or natural log, and you just take the log of both sides. I'm going to take the natural log of 4 to the power of 7a minus 5 equals natural log of 91/3. Now I can use the power property. This exponent is on the entire argument. So the power property says I can move it out in front. And I have this. And then even here, I've got choices. It's easy to isolate the a now, but do I distribute first, or do I just go ahead and divide by natural log of 4 to start getting the a by itself? I'm going to go ahead and distribute first. So I get this. And then on the other side, that stays the same. And then I can add the 5 natural log of 4. Oops. So I add on the right-hand side 5 natural log of 4. And then finally, to get the a by itself, I can divide by 7 natural log of 4. And I get this. The reason why, by the way, I wanted to distribute first is, if we think about it, if I was going to divide both sides by the natural log, at some point it'd also have to be divided by 7. I didn't want to deal with a complex fraction where there's a fraction inside a fraction. And so if I distribute first, notice I never had to deal with that. So these are equivalent. They don't look the same, but they are equivalent. And if you were to type them both in the calculator, you get the same thing. So it is just one of those things. Honestly, if it was a multiple choice test, I would look at the multiple choice answers. Are they written in the same base as the problem was? Then just around the world it to get the variable by itself. But if all the answer choices are written in a different log, then take that log of both sides. But if it's not a multiple choice question, then your choice. You do it either way. So, all right, so that's solving equations. Now let's look, or solving exponential equations. Now let's take a look at solving log equations. These also come in two flavors, and either every term has a log or every term doesn't. And they're very similar. And the good news is with these, I think, are actually easier than the exponentials. So here's the idea with logs. If every single term has a log, then you want to condense both sides so they're down to a single log. The left-hand side of the equation already has just one log, so I'm going to leave that the same. On the right-hand side, we have two logs, so we can use our properties to condense. When there's a plus sign between the two logs, you can condense them using multiplication. So we get log base 7 of 10 plus a equals log base 7 of a times a minus 8. And now it's kind of like equating the bases above. We have a single log on both sides with the same base. So if the log base 7 of this equals log base 7 of that, this has to equal to that. Equate the arguments. You get 10 plus a equals a times a minus 8. And then just solve whatever it is. In this case, it's going to turn out to be quadratic. If I distribute the a, I get a squared minus 8a. Set it equal to 0. I'm going to subtract a from both sides and subtract 10. This will factor into a minus 10, a plus 1. Set each factor equal to 0, and we know a is going to be 10 or negative 1. Now, there is one catch when you are solving log equations. You have to check for extraneous solutions. But the good news is checking for extraneous solutions is pretty straightforward. Take them one at a time. So we have 10. Just go back to the original problem and make sure none of the arguments are 0 or negative. Remember, your argument has to be positive. So if a is 10, 10 plus 10 will be positive. 10 minus 8 is positive. Oh, and this one, 10 is positive. 10 is going to be a keeper. If I try negative 1, 10 plus negative 1, positive. Uh-oh. Negative 1 will make this negative. It's going to make this argument negative as well. Once it makes one argument negative, it is extraneous. That is not part of your answer. So in this case, our only solution is a equals 10. So you just have to remember to check for that. All right, final problem. What if there's at least one term without a log? Well, the easiest way to solve it is get everything with a log on one side and everything without the log on the other side. So I'll get the logs on the left side. I have natural log of x plus 3, and I'm going to move this log to the other side by subtracting it. So it'll be minus natural log of x plus 2. And then I already had the 9 on the right-hand side. I want to move this plus 5 to the right side, so I'm going to subtract 5. And then you may already be seeing it. I'm going to condense the left using the quotient property. And then I just simplify the right. And now we can around the world it. So e to the fourth power is equal to x plus 3 over x plus 2. And, oof, this one's pretty awful. But let's keep going with it. We're going to get the x by itself. So I'm going to go ahead and multiply both sides by that denominator of x plus 2. And I'm going to distribute on the left. So I have x e to the fourth plus 2 e to the fourth. And on the right-hand side, the x plus 2's will cancel out. And I just have that. Now we have an x in multiple terms, so collect all your x's on one side of the equation and everything without the x on the other side of the equation, because then you can factor out your x. And then finally, divide. So there is our answer. And that is our calculator ready form, ready to type in on the calculator. Notice I have not used the calculator to solve these equations. If I need a decimal approximation, I would wait until the very end to get it in this form or whatever form I had for the problems above and then plug that into the calculator. I don't want to introduce any rounding errors. But there you go. There's logs and exponents in a nutshell. Have fun, and I'll see you later. Bye.